Hi guys, this is Miss Bennett. I'm going to teach you a little bit about nuclear chemistry and what's going to be important on nuclear chemistry. The types of nuclear change that we will be talking about are nuclear fission, nuclear fusion, and radioactive decay or half-life. We have talked about half-life a little bit, but we will continue to talk about it today. Here are some videos that if you'd like to go to, you're more than welcome to. These just shows different disasters going on with nuclear disasters. All right, so let's start with nuclear fission. Nuclear fission occurs when you have an atom or a nucleus splitting into smaller parts. So nuclear fission is the splitting, and when it splits, it's going to release particles, nuclear particles. In this case that we're showing you here, it's emitting some neutrons out. You could also have different decay, and we're going to talk about those in just a minute. Once again, there's another video you can take a look at. A nuclear power plant, there's lots of nuclear power plants around the United States where we can get nuclear energy from. It's a much more efficient way of getting electricity. It does use uranium for those nuclear power plants. You do not need to know how it works for this course. Nuclear fusion, on the other hand, is where two or more come together and fuse to one atom. This is a large explosion, like stars, for instance, our sun. Just to review, when we're talking about nuclear reactions, we're talking about the protons and the neutrons in the nucleus. Remember, protons have a positive charge, neutron is neutral, and of course the electrons are out in the electron cloud with a negative charge. Also, just to review, isotopes, remember, are atoms of the same element, but they have different numbers of neutrons, which results in a different atomic mass. Remember, the top number is the atomic mass when we wrote these symbols, and the bottom number is the atomic number. Remember, the atomic number is the number of protons. The atomic mass is the number of protons plus neutrons. Radioactive decay that causes radioactivity are when these unstable nuclei break apart and emit one or more particles and some energy. And the particles that we will be talking about are here in this chart. The proton, the neutron, an alpha particle, a beta particle, a gamma particle, and a positron. The proton, if you will notice, has several different symbols. The ones that we use the most are probably these two. The top number is the mass, and the bottom number is the charge. So a proton has 1 AMU for the mass, atomic mass unit, and a positive 1 charge, which looks exactly like a hydrogen from the periodic table. The proton, if a proton is emitted, you can stop those protons with a few sheets of paper. A neutron, several different symbols again. The one that we use the most is this one. The neutron has a mass of 1 and a charge of 0, neutral charge, can be stopped by a few centimeters of lead, more dangerous than the proton. An alpha particle, the most common symbol that we use is the alpha symbol, the Greek letter, and the alpha looks just like a helium. And what happens is the unstable nucleus releases 2 protons and 2 neutrons. These are least dangerous, and they are stopped by paper once again. The beta particle, or the beta, that's the Greek letter beta, is also the same as an electron. can be released. And what happens is a neutron, being neutral, has no charge, is basically a proton plus an electron together. So when that splits, we get the electron emitted from the nucleus. This can be stopped by heavy clothing. So once again, not very dangerous to us. Okay. Now the gamma particle, or the gamma rays, this is a gamma in the Greek letters. It does not have a specific structure like you see in these other four, and it is the most dangerous, and you have to have lead to stop it. We also have a particle called the positron. The positron is the exact opposite of a beta particle. The beta particle being the electron. The positron is a positive electron, and that's the nuclei with too many protons can become stable by emitting those positrons. Once again, stopped by heavy clothing. You will need to know these symbols in order to balance nuclear equations, which is what our whole goal is for knowing these. So we are going to balance some nuclear equations just like this, okay? So the first thing that you need to recognize is, yes, this is a helium, but that is also an alpha particle. So we have alpha particle being emitted, or alpha decay. When you balance these equations, the arrow is kind of your dividing line. The top numbers that are over here and over here must be the same. So if this is equal to 222 over here, this over here has to be equal to 222. So what I would ask myself is 4 plus what gives me 222, and that would be 218. The two bottom numbers have to be equal to the numbers that are over on the left side, and in this case it's 86. So 2 plus what gives me 86? It is 84. So this is the mass number, this is the atomic number. So I look up on the periodic table, and on the periodic table, number 84 is polonium. So now I have a balanced nuclear equation. All right, let's try another one. It says, what product is formed when polonium emits an alpha particle? So I take polonium, which is PO, and it's polonium with a mass of 212. Polonium is number 84 on the periodic table. If it emits an alpha particle, remember, is nothing more than a helium, mass number 4, atomic number 2. We want to know what's being left. So over here on the left side, we have a total of 212. Over here on the right side, we also need 212. So what plus 4 gives me 212? 208. Over here on the left side, we have a total of 84. So I need 84 on this side. 84 on this side, 2 plus 82 gives me 84, and number 82 on the periodic table is lead. Let's try these. Once again, we have polonium going through an alpha decay. Alpha decay. So 4 plus what's going to give me? 218. So 214 will give me, plus 4 gives me 218. Over here I need 84. 2 plus 82 gives me 84. And 84 on the periodic table, once again, is polonium. So we've got 2 isotopes of polonium. Okay, we're going to take PM, which is promethium, through a beta decay. And remember, a beta decay is nothing more than an electron, no mass, and a negative 1 charge. So over here I have 142. Well, 0 plus 142 That would be equal. Over here I have 61. What plus -1 gives me 61? It would be 62. Watch your integers. Number 62 on the periodic table is samarium. So be really careful with that -1. Okay, this third example. 253 plus 4 gives me a total of 257. So I need 257 on this side. 1 plus 256 gives me 257. On the bottom, the total is 99 plus 2 gives me 101. So I need 101 on this right side. 0 plus 101 is 101. So on the periodic table, 101 is MD Mendelevium. All you've got to do is make sure the numbers are equal on both sides. They add up to the same thing to balance these chemical equations. Now, let's try one more. I want to add one in here. What if you have something like this? 21484 polonium added to 2 alpha particles and 2 electrons. And we want to know what we're going to get over here. If you have a big number 2 out here, that means I have 2 of these. So I would need to multiply to get this top number. 2 times 4 is 8. 2 times 2 is 4. 2 times 0 is 0. 2 times -1 is -2. So over on this left side, I have 214 plus 8 plus 0, which is 222. So I need 222 on this right side. 84 plus 4 is 88. 88 plus a -2 is 86. So I need 86 on the right side. If I look up on the periodic table, number 86 is radon. So that is for balancing chemical equations.